Yeah, good evening to all of you. Welcome to the Basic Electronics video lecture series. In this video lecture, let me introduce bipolar junction transistor. But before that, let me have a quick overview what we have covered so far. If we have a look at the syllabus, so this is the syllabus copy that I am presenting to all of you. So we have covered diodes and their applications. Okay, so let us have a quick look what are the topics that we have discussed. We have covered diode operation, forward and reverse bias characteristics, reverse bias operations, and then followed by voltage current characteristics of a diode. Shortly we call as a VI characteristics for forward bias and VI characteristics for reverse bias we have seen. Then subsequently we have discussed rectifiers, specifically the half-wave rectifier and full-wave rectifier. That comes under the topic called rectifier, the basic DC power supply block diagram we have discussed, and then followed by half-wave rectifier. Just to zoom that so that you can see neatly. Okay, so we have discussed a block diagram of DC power supply and explained each and every block, how it is useful in converting AC power to DC power. The rectifier part, we have seen half-wave rectifier operation. Then you are told advantages and disadvantages of half-wave rectifier operation. Then followed by we have full-wave rectifier. In this full-wave rectifiers, we have discussed two types of full-wave rectifiers, namely center-tapped full-wave rectifier. We have discussed its operation and even the input-output waveforms of center tapped full wave rectifier, and we have discussed even merits and demerits of center tap full wave rectifier. Then followed by bridge full wave rectifier operations also we have seen. uh, Again, there are specific advantages in the bridge full wave rectifier operation. Then followed by the power supply block diagram, and then further we discussed filters, how to smoothen the pulsating the DC voltage of rectifier through the filters. We have seen that, and later we discussed regulators, which specifically we discussed capacitor input filter, and then followed by voltage regulators. And we have seen different types of percentage regulations, namely the line regulation and load regulation with reference to the regulations. Then followed by, we discussed an important a Zener diode. Okay, so which is specifically operated in a reverse bias. So we introduced the Zener diode, then followed by we discussed the Zener breakdown, and we looked into the various applications of Zener diode. Okay, so Zener regulation with a variable input voltage, and the Zener regulation with variable load, and many worked examples we have seen while covering all these topics. Okay, so though the total hours prescribed is 8 hours, I think approximately we have taken the same amount of time to cover all the topics of diodes and their applications. So in the textbook, which is prescribed, the students are advised to go through the following sections. So now it's time to discuss the second module, which is in this module we have two chapters, namely bipolar junction transistors and field effect transistors. So these are the important transistors that any electronic students need to understand. BJT, first we'll cover BJT, then followed by this BJT we discuss field effect transistor. Okay. Broadly in BJT, we are going to cover bipolar junction transistor structure and BJT, basic BJT operation, different types of biasing, the operation of transistor, then followed by transistor currents. Then subsequently, we will look at BJT characteristics and the various parameters like the beta, alpha, all these things, DC beta, DC alpha, and later we will see the BJT circuit analysis in the common emitter mode, and the collector characteristics we are going to discuss, the curves and different regions of operations, namely the cutoff region, saturation, and even the active region. Then later we'll see how to draw the DC load line so that BJT can be used for different applications. The main application that we are looking at is the BJT as an amplifier, and later we will discuss how to get voltage amplification from the bipolar junction transistor. So these are the various topics that we are going to cover under the bipolar junction transistor. Okay, so let me now present a textbook. From that, let me discuss the various topics of bipolar junction transistor. So bipolar junction transistor, very important topic in the basic electronics course. So shortly we call a bipolar junction transistor as BJT. Okay, so it is a BJT, bipolar junction transistor. When we look at the chapter outline, as per our syllabus, we need to cover bipolar junction transistor structure, that is section 4.1, then basic BJT operation, section 4.2, BJT characteristics and parameters, section 4.3, section 4.4, which is the BJT as an amplifier. So these are the topics that we need to cover under the chapter bipolar junction transistor. So let us have the key objectives of this chapter. So before that, let me zoom a little bit so that you can see the content clearly. Okay, fine. The key objectives of this chapter is we need to describe the structure of the bipolar junction transistor. Okay, the internal semiconductor structure we are going to explain with reference to the bipolar junction transistor. And next we are going to discuss the operation of a bipolar junction transistor, how the transistor works, how it functions, and so that we can use it for various operations. So then later we are going to discuss BJT parameters, characteristics, and even analyze the transistor circuit, simple transistor circuits. Then followed by we need to discuss how a BJT, bipolar junction transistor, can be used as a voltage amplifier. So these topics doesn't fall under our syllabus. Therefore, we cover the key objectives that are related to our discussion is for the first four up to the use of the BJT as a voltage amplifier. Okay. Then followed by we have a key terms. So students need to understand what do we mean by bipolar junction transistor, and we need to understand the terminals of a transistor, namely the emitter, base, and the collector. So we'll discuss why the terminal is labeled as emitter and why the another terminal is called as a base and the collector. And we'll see the gain of the bipolar junction transistor. That's very important to use it in various applications. And we have gains in different configurations, namely the beta, alpha, all those things we're going to discuss. And the BJT can be used in different modes of operation. So namely the saturation mode, and we have a linear mode, and then the cutoff mode. So all these things we're going to discuss. Then followed by the load line analysis is very important to understand the various applications of the bipolar junction transistor. So these are the key terms students need to go through, so to understand the fundamentals of bipolar junction transistor. Now to understand in more depth and demonstrate the circuits under this bipolar junction transistor, I advise the students to use any one of these softwares, either the multisim or the LT Spice software. So that is a freeware, so that it's an open source that can be downloaded from the LT Spice the site. Just Google it, the LT Spice, so you will find the download link, and you can download this software and you can install it. So in my desktop, the laptop, you can see that I've already installed LT Spice here. In the coming classes, I'm going to discuss how to use this software for to construct the simple circuits and simulate it in the using the LT Spice. Okay. So then comes the introductory part of the transistor. The invention of the transistor was the beginning of the technological revolution that is still continuing. Even today, we keep talking about BJT. That is that we can call as a technological revolution in the electronic the sector. All of the complex electronic devices and systems today are an a growth of early developments in semiconductor transistors. So today you can see any electronic applications, and they are a tiny element that is functioning in all the electronic systems is the transistors. So when we say transistor, there are two basic types of transistor that comes into a play. That is bipolar junction transistor. So we will begin the study of this bipolar junction transistor presently. Then later we have a field effect transistor. Shortly we can call as a FET. So BJT and FET are the two basic types of transistor that any electronic student need to go through these fundamentals of these two transistors, so that you can develop simple systems using these two transistors, simple circuits using these two transistors, and later one can build complex circuits, based on the basic elements of the electronic systems are nothing but the BJT and the FET. So these two transistors we are going to discuss in this present chapter. We are going to discuss BJT. In the subsequent chapter, we are going to discuss the field effect transistor. So the BJT is used in two broad areas. What are those two broad areas? It can be used as a linear amplifier to strengthen the weak signal, to boost or to amplify an electrical signal, or it can be used as an electronic switch. So to summarize here, the bipolar junction transistor is used in broadly in two different applications. One is a linear amplifier. It can be used as a linear amplifier. That means as the input signal is increasing, corresponding you can see the strengthened output signal as an output of an amplifier. That is the one application of bipolar junction transistor. The another application is the BJT can be used as a switch. Just it is like a mechanical switch. BJT can be used as an electronic switch. It can perform on and off switch, which is most essential in digital computer. Okay, so even digital computer, the transistor that we are using, it will work either as an on switch or the off switch. Okay, so there the switch role comes into a play when we use BJT as a switch application, electronic switch applications. The major difference between electronic switch and mechanical switch is, at what rate the switch turns on and turns off. Generally, electronic switches takes less time to turn on and turn off compared to the mechanical switch. That's where the BJT is used, okay, as an electronic switch to turn on and turn off. Probably in today's scenario, since computer operates at 3 gigahertz. Okay, so the typical frequency, I mean the time taken by this is the frequency of operation of today's computer, and the time is nothing but the reciprocal of the frequency 1 over f. This comes to around 1 by 3 gigahertz, comes to around time as 0.33 nanoseconds of time. So these are time taken to do simple operations in a computer. This is the amount of time it takes. However, we are not going to use the single the transistor. We are going to use billions and billions of transistor. So therefore, even the today's computer comes with multi cores, and therefore so the time what it takes to do the simple work is it's a negligible amount of time. So that's where the electronic the switches like BJT can switch faster compared to the mechanical switch. All right, so let's look at devices application preview. So here there is small applications which you can students can go through this applications preview of this, and let me now go straight away into the bipolar junction transistor structure. Okay, so before we go to the operation of the bipolar junction transistor, so it's very essential to discuss the structure of the transistor. The structure of the bipolar junction transistor determines its operating characteristics. Okay, so how exactly structured BJT is? It's made up of. Its structure that decides the operating characteristics. Okay, so what do you mean by that? So in this section, we are going to discuss the semiconductor materials that are used to form the BJT, and also you will learn how the standard symbols are available for the BJT that we call standard BJT symbols. We'll see that what is the standard, what do you mean by standard BJT symbols in this topic. So the objectives of this particular section is we need to describe the structure of the BJT and explain the difference between the structure of NPN transistor and even the PNP transistor. So BJT comes with two different types of transistor, namely NPN and PNP transistor. We are going to discuss the difference between them, and also we identify the symbols of NPN transistor and the PNP transistors, and we name the three regions of BJT, and their labels will be discussed. Okay, let us discuss more in depth of BJT structure. The BJT is constructed with three doped semiconductor regions separated by two uh, PN junctions. Okay, so that is shown here in this diagram. I'll come back to this diagram a little later. So it is shown in the epitaxial planar structure. That is the technology used in the manufacturing of bipolar junction transistor. So this bipolar junction transistor has got two junctions. Okay, what are those two junctions? We'll discuss that. And it has got three regions within the bipolar junction transistor. Namely, the regions are emitter region, base region, and the collector region. So as we can see from the name itself, emitter means it emits. Okay, it emits the charge carrier. That's why the name is called emitter region. And the base is acts like a control. And the third region within the bipolar junction transistor is the collector that collects the charges emitted by the emitter. So the symbolic representation of this is emitter can be labeled as E, and the base can be labeled as B, and the collector can be written as uppercase C. So these are the various terminals or regions of a transistor. So they are analogous to the vacuum devices like okay, anode, okay, and we have a cathode, okay, and we have a grid. So these are the various the regions in the old devices like vacuum tubes. And now in BJT we have emitter, base, and collector. And similar thing we have even in FETs also. FET, when you have a look at field effector transistor, just like BJTs, we have a terminal. See, emitter is analogous to the source, which we call as S here, and the base is analogous to the gate. So that is the analogous equivalent, and the collector is analogous to the drain here. Okay. So all these three, these are the very old, the vacuum tubes. That's how the BJT has been, invented, and the terminals remain same, analogous to the emitter, base, and collector. Okay, so in the same way that we have FETs as source, gate, and drain. Okay, so these are the various terminals as structure of the BJT. Physical representations of two types of BJTs are shown here. One type consists of two N regions separated by the P region, which we call NPN transistor. As you can see here, there are two N regions here. This is one N region, this is another N region. Two N regions are now in mid region. We have a base region, which have a P type, and this type of transistor is called as NPN transistor, where two N type of semiconductors, or you can say another way, a P type of semiconductor is sandwiched between the two N type of semiconductor. So this forms the NPN transistor. And then we have other type of consists of the two P regions. As we can see here, two P regions are here, and there is separated by a single N region, that is which you see in between here, N region. So we can say that the N region is now sandwiched between two P type of region. That forms the PNP transistor here. And why the term bipolar is because of these devices, either NPN or PNP transistor, uses both type of charge carriers, namely the holes and the electrons. They act as a current carriers within the transistor structure. Okay, that's why the name is bipolar junction transistor. Okay, so if we have a look at this basic epitaxial planar structure here, we start with substrate. Substrate acts like a foundation material to build the transistor. Okay, this acts like a foundation. Okay, so over this we build the different layers, namely we have a collector layer, collector region, and then we have on top of it we have a base region, then we have a emitter region. But the substrate is also a semiconductor. This can be of either N type or P type semiconductor. And if we dope it with suppose if I want to build NPN transistor, the emitter will be of N type and the base will be of P type, and again collector will be of an N type. So now we need to build a collector region. So therefore we either we can take N type or P type, but here we dope with uh, the pentavalent impurity that forms the N type collector, and on top of it again we dope it with the trivalent impurity that forms the P type base, and again on top of it we again use the pentavalent impurity to form the emitter. And once these three regions are formed, okay, collector, base and emitter, a metallic contacts are attached to each region. Okay, as we can see here, that this is a metallic contact attached to the collector region, and here we have metallic contact attached to the base region, and lastly we have a metallic contact here, which you see in a color, gray color, that is metallic contact that is attached to emitter. And then we take out the leads out of these metallic contacts to the three leads from each region that forms, the collector from the inner region, and then the base from the middle one, and then the emitter from the outermost. Okay, so this forms the three terminal device. So BJT is a three terminal device. So you can write it here. The BJT is a three terminal. It has got a three terminal device. It has got three terminal device, and also we said BJT has two junctions. It has got two junctions, and it has three terminals. Namely, what are those three terminals? We have three terminals like emitter. Let me start with the outer one: emitter, comma base, which is the middle, and then we have a collector. So we have a totally three terminals. Okay, so now we have a two junctions. Namely, what are those two junctions? Either NPN or PNP. We can find two junctions. One of the junction can be called as a base emitter junction. The junction between the emitter region and the base region, or base and emitter region, can be called as a base emitter junctions. Let me write it here once again. What are those two junctions? One is the base emitter junction, so that is the one junction, and another junction what we are seeing is the base collector junction. So junction formed between the base region and the collector region is called base collector junction. Let me write it here. The other junction is base collector junction. Now current has to go through, the current which is a charge carriers emitted from the emitter has to go through the two junctions, namely the base emitter junction and the base collector junction. So they offer some resistance here, and of course, how we bias these two junctions, we'll see that later on. How do we bias the base emitter junction? How do we bias the base collector junction? In what way, if we bias these two junctions, so it leads to the current flow from, charge carrier movement from emitter to the collector. Already told you about, how this three terminals functions. Charge carriers are emitted from the emitter, and it is collected by the collector, and this charge carriers, the quantity of charge carrier, the amount of charge carriers moving from emitter to the collector is controlled by the base terminal. So this acts like a control. Okay. Diode is actually two terminal device where we don't have any control for the current to flow. Diode is a unidirectional device. So we already discussed about that in module 1. So diode conducts current in one direction, that is diode conducts current in forward bias, and blocks current in reverse bias. So it is a one-way device. Okay, so this is the working principle of diode. Okay, so diode conducts current in forward bias direction and doesn't conduct current in the reverse bias direction. Okay, this device doesn't have any control, whereas here the BJT has now got three terminals. It is just like we can represent it with a switch. Okay, in this way. Suppose if the charge carriers or current is flowing from top to bottom, the current can be controlled through the third terminal, which is called, in our case, which is called as a base, and here we have an emitter, and we have a collector here, and the current from the collector to emitter, or charge carriers from emitter to the collector, can be made either 0 or it can be made as max. So that all depends on the what is the base current we are going to provide. Okay, so base acts like a control. The current movement from the collector to emitter can be either made as zero or it can be made as maximum, whatever the value we are interested in. Current flow from the collector to the emitter that can be controlled through the base. That's how the transistor BJT functions. So even the whatever I'm saying with reference to NPN transistor, equivalently it is applicable to the PNP transistor. Okay, so students can just connect it with the PNP. Though I mentioned here the BJT is made up of two junctions, so equivalently even NPN PNP transistor also has two junctions. So namely the base collector junction and the base emitter junctions. Okay, so this also has got three terminals here. The only thing is the difference between NPN and PNP is the semiconductors used inside them. Okay, here we have two N types and the one P type that separates the two N type semiconductor. Whereas in PNP transistor we have a two P type semiconductor and separated by the one N type semiconductor. So this is how the structure of a NPN and a PNP transistor looks like. Okay, so we discussed about how the bipolar junction transistor is manufactured and its symbolic structure. This is the structure of the NPN transistor and this is the structure of the PNP transistor. Now let's have a look at the symbol of the PNP transistor here. Okay, let me read out a few points for you here. The PN junction joining the base region and the emitter region is called a base-emitter junction. We already discussed about that. The PN junction joining the base region and the collector region is called as base collector junction. Okay, that is already shown. And a lead connects to each of the three region is also shown. These leads are labeled as emitter, base, and collector. Okay, for emitter, base, and collector respectively. The doping point is very important again. The base region is lightly doped, so that is the one which controls the current flow from charge carrier movement from emitter to the collector. So therefore, the base region is lightly doped. Lightly doped in the sense there are less number of charge carriers available in the base region. Okay, and it is very thin, of course. And then we can see the emitter region, which is heavily doped. Okay, you can see more number of charge carriers in the emitter region because that is heavily doped. More the doping, more charge carriers. Okay, the electrons or holes, whatever may be. Doping, if I say heavily doped means that means more number of charge carriers can be found in that particular region. And lastly, we have a collector region which is moderately doped. So medium amount of charge carriers you can find in the collector region. So doping is very important. Let me summarize this what we are trying to say. So emitter is heavily doped, and base is lightly doped, and lastly the collector is I'm just showing here the LEDs, the labeling part. The collector is moderately doped, Okay, in this way the doping structure of the BJT is shown. So because of the difference in the doping levels, the emitter and the collector the terminals or LEDs, they are not interchangeable. Okay, you may ask a question here, can we interchange this emitter and collector or collector and emitter? No, it's not possible here because emitter we already said about it. Emitter is heavily doped, the collector is moderately doped. Therefore, these two terminals here, collector and emitter, these two terminals cannot be interchanged because emitter now in the circuit, the way we connect it here, this is the one which has got heavily doped and this provides required amount of charge carriers. And we can't interchange the emitter and collector. That thing, the student should keep in mind. Whether it's the NPN transistor or PNP transistor, it doesn't matter. But these two things are not interchangeable. The emitter and base, collector is not interchangeable. That's what it is mentioned here. okay, because of the different doping here. And here we have a schematic symbols, okay, standard symbols of bipolar junction transistor. I would like to go through this standard symbols. Okay, so the standard symbol of BJT, as you can see here. Okay, so this BJT can be viewed even as a two diodes connected back to back. Okay, suppose if I have a diodes like this. Okay, so what type of transistor this is? Can you just see, think about it? Okay, so I'm just connecting diodes, two diodes in this way. And another way which we can connect diode is cathode to the other side in this way, and cathode to the other side, and again here. Okay, so we have here p type, n type, and for this particular diode we have a p here and a n here. Okay, so this forms a PNP. It is equivalent, that's all. So a transistor can be equivalent to the PNP transistor. This transistor can be made equivalent to this, and NPN transistor can be made equivalent to this. And we can visualize NPN transistor as two diodes connected back to back, or PNP transistor as two diodes connected back to back. So here we have a PNP, which you can call, one of them is called, can be called as emitter, collector, and base. And similarly, here we have a P type here for this diode, P type for this diode, and the other side we have an N type and N type here. So this can be called as emitter, collector, and base. This is one of the ways, which you can visualize the transistor as a diodes connected back to back. Okay, now let us have a look at the standard bipolar junction transistor symbols. So this is a symbolic representation of the transistor. As we can see, there's an arrow mark here, which you can closely observe it. The arrow mark is seen here. The arrow mark shows the direction of the current when the base emitter junction is forward biased. When we forward bias this base and emitter junction positive to here, and this is an NPN transistor. I must connect it in opposite way. Okay, so this is NPN transistor. So we have N type, P type. I think I've connected correctly. N type. So positive here and negative here. So this forward biases the base emitter junction. Okay, so base emitter junction. When we forward bias the base emitter junction, the arrow mark indicates the direction of the current. Okay, therefore arrow mark plays a very key role in the identifying the emitter terminal, because it's very important to identify emitter terminal, because as I said already, collector and emitter cannot be interchanged. Therefore, identifying the emitter plays very important role. When the base emitter junction is forward biased, the arrow mark indicates the direction of the current. Okay, so this is the arrow mark here. So when the emitter is identified, the other terminal will be the collector, and base is emitter, which is acting like a control terminal. And similarly, the same thing applies whatever we said about NPN transistor in the standard BJT symbol for the PNP transistor's arrow mark is inward, and this again represents same thing. So when this is a PNP transistor, so we have a collector is of P type, and base is of N type, and emitter is also a P type. So when we forward bias this, connecting negative to the base and the positive to the emitter, so this forward biases the base emitter junction, and arrow mark indicates the direction of the current. So here current direction is inward, inside the BJT, whereas here current direction is outside it is coming here. Okay, when the base emitter junction is forward bias. So this is how the BJT the standard BJT symbols looks like. Arrow mark, based on arrow mark, we can indicate, we can identify as an emitter terminal. In the commercial devices, students can identify the terminal, because there will be some indication will be given by the manufacturer to locate this emitter and the base and collector. Otherwise, it becomes difficult. If you connect it randomly, the device will not functions properly. So, therefore, the identifying terminal makes sense. Okay. And before we move to the next section, I just want to discuss about appreciate the people who invented the bipolar junction transistor. The transistor bipolar junction transistor was invented in 1947, by the team of scientists at Bell Laboratories, USA. So this was invented at the Bell Laboratories, USA. The three persons were William Shockley, Walter Brattain, and John Burden. These are the three scientists, team of scientists who invented the bipolar junction transistor in the year 1947, and they developed the solid state device, and that was the replacement of uh, vacuum tube, and each of them received a Nobel Prize in the year 1956 for their great invention, which is nothing but bipolar junction transistor. And the transistor is arguably the most significant invention of 20th century. Of course, it is a very great invention of the 20th century, and they have been awarded the Nobel Prize for their significant invention. Okay. Okay, that's about the basics of bipolar junction transistor. Now it's time to look at the BJT operation, basic BJT operation. In order for the BJT to operate properly as an amplifier, we already said about BJT applications are of two types. One is it can be used as an amplifier, or it can be used as a electronic switch, fast electronic switch. It can switch, turn on and turn off very fast. Okay, maybe million and billion times within a second that can be done. So these are the broad applications of transistor. So let us see that how, in what way we can use BJT as an amplifier. Amplifier means it which strengthen the weak signal. If input signal is very weak, I mean which is going to be in a sinusoidal AC signal which is in microvolts or millivolts, okay, very small signal, and this can be boosted to the larger level, okay, to the volts level here. Okay, so volts means if it is a millivolt, and if we increase, if we use an amplifier and strengthen that to volts, that means it is 1,000 times the signal has been strengthened, 10 to the power of 3 times the signal has been strengthened. Such a way the amplifier can be used. So the basic element that strengthens the small signal to a large signal like this is the bipolar junction transistor. And in this chapter, we are going to see that how the BJT is responsible to make a very large signal like this when we apply a small signal or weak signal in terms of the microvolts or millivolts. Okay, so switch part we'll discuss. That doesn't come under our curriculum and the syllabus, so therefore we are leaving that part as it is. So BJT to operate smoothly as an amplifier, the two PN junctions we already discussed inside the structure of a bipolar junction transistor. It is made up of two PN junctions. They must be correctly biased. Okay, so if you don't bias it properly using some external DC voltages, so bias means we need to apply uh, the bias properly. Either you have to forward bias one of the junction and reverse bias the other junction using some external voltages and polarities that we connect through the external voltage. That's very important, because if you do it in other way, the device that doesn't work like an amplifier. So in this section we mainly use NPN transistor for illustration purpose. Okay, so as I told you already, if you understand one type of transistor, then understanding the other type of transistor becomes very easy for you. So next is the operation of the PNP is also same as the NPN, except the roles of electrons and holes. They change, the roles of these two changes. So NPN transistor majority charge carriers are electrons, and in PNP the majority charge carriers are holes. The roles will interchange when you switch to PNP transistor, uh, where holes becomes a majority charge carriers. And even the bias voltage polarities also keep changing when we move from NPN to PNP, and even the current directions also keep changing when we move from NPN transistor to PNP transistor. So at the end of this section, students will be able to understand the basic BJT operations. Previously, we discussed about structure of a BJT, and now it's time to look at how BJT works, because this is a fundamental element, okay, which can be used in two different types of major applications, which is amplifier and a switch. So one need to understand the BJT operation to understand its usage as an amplifier and a switch. And we need to describe the forward bias, forward reverse bias. So this is the mode for which the BJT works very well. You'll see that which one has to be forward bias and which junction has to be reverse bias, so that if you understand the bias mode properly, then the BJT can be understood very well. And we show how to bias the PNP transistor and how to bias the NPN transistor with the DC sources, and explain the internal operation of the BJT, because here internal operation plays a very key role. We need to see how electrons moves and holes move within the BJT. Okay, that's very important. We need to discuss the hole movement, electron movement within the BJT, so that to understand the overall BJT operation. Next important thing is the currents. Okay, so simply understanding the charge carriers doesn't make any sense. We need to also look into the directions of the current here. Calculate any transistor currents if the other are I'm sorry, because of Diwali festival here, huge cracker sound you are going to hear. You are hearing. Okay, fine. So we need to look at the directions of the currents also. We need to identify currents. It's very important. So these are the things which gives you the preamble for the BJT operation. Okay. And the students, if you have any questions, you can just ask me before we move to the other topics, other sections. Any questions? All right, if you don't have any questions, let me move and to the next section and explain you how exactly BJT can be biased. Here we have a figure shown in 4.3, which shows bias arrangement of both NPN transistor and the PNP transistor for operation as an amplifier. So let us assuming that we are using BJT as an amplifier. Here we have a bias arrangement. This is the bias arrangement for the NPN transistor, and here we have a bias arrangement for the PNP transistor. And here we use a type of bias arrangement called as a forward reverse bias arrangement for the bipolar junction transistor. Okay, what do we mean by that? We'll discuss it. Notice that in both the cases, base emitter junction, which we call as a B junction, is forward biased, and the base collector junction is reverse biased. Okay, this condition is called as a forward reverse bias condition. Okay, let's have a look at here. So here we have a DC power supply. So this is a DC supply. Okay, and here also we have a DC supply. When you represent it with a long line and short line here, that shows it is a DC supply. Okay, we have a two batteries here, DC batteries supplies. Okay, here also we have a DC supply. And I look at the polarity in what way it is connected. First of all, this type of transistor is NPN transistor, because arrow mark is outside. So this is a NPN transistor, and then you can see that there is a current limiting resistor here used here, so that this is a NPN transistor. Therefore, the collector is of N type, base is of P type, and again the emitter is of N type. And check the polarity of the power supply connected here. This ground is so they're virtually at different places. This point is same as this point. So now we can see positive is going to the P type, I mean the base region. It is also a P type, and also as it acts like a base. And here we have an emitter which is grounded, and even we have a collector here which is also an N type here. So now we can see here base is connected to the positive supply, and this is of a P-type semiconductor. This is forward biased, and even the emitter terminal is connected to the negative. Okay, you can see the polarity is plus and minus here. So we can say that the base emitter is forward biased. Okay, let's have a base collector now. Base and collector here. So the collector, we can see here the collector is of N type, and it is connected to the positive supply. So therefore collector and with reference to the base, okay, base is already of a p type connected to the positive here, so therefore base collector is reverse biased. Okay, so it's very important to use npn transistor as an amplifier, so therefore we need to maintain this condition, otherwise it won't work as an amplifier. You may ask a question here, can we do reverse? It won't work if you do it reverse. Reverse biasing the base emitter and the forward biasing the collector, it won't works. Of course, there are different types of bias which you can check it. If you have a LT spice, so what is that base emitter junction and the base collector junction? Okay, what are the types of bias you can apply? You can either forward bias both, that is the one type of bias, or reverse bias both, that is another bias which we can try and check what how exactly transistor works. And right now what we are seeing is base emitter is forward biased, collector emitter is reverse biased. And what if the reverse biased base emitter junction and forward biasing the collector junction, base collector junction? So among all these different types of biasing, the only bias that works, that can be used this device for applications such as amplifier, is the forward biasing the base emitter junction and reverse biasing the base collector junction. Okay, you can check it, but however I'm giving you the hint here. Other type of bias, the device is not going to be useful. Okay, so these are this type of bias, the device is not going to become useful here. Only this bias, okay, the base emitter junction forward bias and base collector junction reverse bias. So already we are seeing here, so we have already biased this complete circuit in the with the base emitter forward bias and base collector as reverse bias, and this complete configuration works like an amplifier. Okay, so this is the mode, the circuit, the structure that can be used as an amplifier. Of course, with these elements, we cannot do amplification. We need to have a capacitors connected, and we need to have a biasing arrangement properly, so that okay, this efficiently works as an amplifier. That we'll see in the coming classes, how to construct, how to design BJT for doing amplifying action. Okay, so this is a simple circuit, and so now the BJT is ready for doing amplifying action. But here we have not shown AC signal, because we only shown here the bias arrangement. And if you apply AC along with DC, then definitely this structure will work like an amplifier. And let's have a quickly look at this PNP transistor, how it is biased. So PNP transistor, this is emitter is of P type, and also this is going to be the emitter, and the base is of N type, and this is also going to be the base, and the collector here is going to be of again P type, and it's also collector. Okay, so in this way, so it is implicit that we need not write always the emitter, base, and the collector. It's understood that arrow mark indicates emitter, the other side it indicates collector, and there is a base which is acting like a control. Okay, you need not write every time the emitter, base, and collector, and you need not write even the P and P always. So it is understood that the structure, as if it is a arrow mark is inside, it is a PNP transistor. And now junction between the base and emitter, so that is forward biased. You can see the power supply, how it is connected. So here we have a negative terminal connected to the base, which is of N type, so it is forward biased, whereas the emitter, which is of a P type, connected to the positive. As I told you, these two are at different places, though they are at different places, virtually different places. This point is same as this one. Okay, so now this emitter is connected to the positive supply. So we can also write circuit like this, also making single ground. Okay, we can do that. Okay, so the emitter is connected to the positive, therefore base emitter junction is forward biased. Let's have a look at base collector junction, whether it's reverse biased or not, with the help of this power supply. Okay, so base collector junction. So you can see the base here. Base is already tied to the negative. So it is the base is here is of negative, and look at the collector. Collector is of the P type, that is connected to the negative. So now this is going to be reverse bias. So this is a power supply that reverse biases the base collector junction, and here we have a power supply that forward biases the base emitter junction. So you may ask a question here: do we need really the two power supplies to do the forward bias the base emitter junction, or and the reverse bias the base collector junction? It's really not required. So we'll see in the coming classes how to bias base emitter in the forward and base collector in the reverse using single power supply, because in electronics using two power supplies and too many wires, too many resistors is not good. So therefore we can even use a single power supply and bias these two junctions with forward and reverse bias. Okay, so this is the bias arrangement for the both NPN and PNP transistor. Okay, so we'll stop at this point, and so that if there are any questions related to the today's class, students can ask. Otherwise, we'll stop it at this point. In the next class, we'll continue with the BJT operation and as well as the characteristics. Any questions are there? Any doubts? So if there are no doubts, let me stop it here and continue in the next class. Thank you for watching.